students. Today we will be talking about uh, carbon nanotube based CNT based partial confinement actuators. It has been observed that a single-walled carbon nanotube means if you have a graphene sheet like this, and if you roll it, depending upon the chirality of the vector, you convert it into a nanotube, and this nanotube can deform when electrically charged. Deform when electrically charged. That means if this is the original carbon nanotube, and so if you apply a negative voltage, it will turn. So it is 0V. Application of negative voltage will make it bend in this way. Application of positive voltage will make it turn in this way. So this property of this carbon nanotube is used in making an actuator. Now, an actuator consists of two sheets of single-walled carbon nanotube nano paper. So actuator consists of two sheets of single-walled carbon nanotube, and they are called paper. And this nanopaper, which is held together by insulating double-sided Scotch tape. So we have one nanotube, and in between there's a Scotch tape, and two nanotubes together, two sheets of carbon nanotubes held together. And this insulating, this Scotch tape, and there is also an insulating plastic lamp upper end which supports the paper and holds electrical contact in place. There is an insulating plastic clamp which at the upper end which supports the paper. And holds the electrical contact in place. Now, after that, the sheets are placed in 1 molar NaCl solution. The sheets, and the paper, whatever you may call it, and they are placed in 1 molar NaCl solution, and a few volts are applied, which causes a slight deflection. So this is slight deflection is caused by application of few volts of the order of centimeters. So this deflection, what it does, it changes the polarity of voltage. Or rather, we should say that a change in polarity of the voltage also causes the deflection to occur, but occurs in the opposite direction. Is reversed. Now, if we apply instead of DC, if we apply alternating current, so this process of reverse deflection will keep on. So we will get AC consists of oscillating electric voltages. So this will cause a biomorphic cantilever actuator. This will lead to a biomorph cantilever actuator. Now, these actuators are nano-sized. Since we are using carbon nanotubes. Now, if we use, instead of 2, if we use 3 single-walled carbon nanotubes with 3 fibers aligned, 2 outer and 1 inner, there will be 2 outer fibers, which is metallic, and there will be 1 inner, which is an insulator. And the 3 fibers aligned on the 3 nanotubes, they will be in axis parallel or in contact. Now, the resonant frequency associated with the vibration of these actuators based upon carbon nanotubes So this is the clamped one. It will cause oscillations due to this oscillating AC wave. So there will be a frequency. So that resonant frequency is given as equal to E by rho to the power 1 by 2 into B by L. E is the elastic modulus. Rho is the density. B is the beam thickness. And then there's the beam length. So this is your L and this is your B. So if you plot a curve with resonant frequency versus the area, area square or length square. So if you plot F0, which is in kilohertz, versus length square, which is in millimeter minus 2. That means basically we are having a plot between F0 and L square. So we get a linear plot, and linear plot is nothing but if you take the slope, it will turn out to be this quantity. And this frequency, resonant frequency, finding a resonance frequency, and this whole clamp beam and all, they have variation in MEMS cantilevers. Now, coming to the electrical aspect, if you concentrate on the conduction that is taking place in the system, applying voltages and causing deflection. So, if you go into deep, so the valence electron they dissociate from their atoms and become delocalized. The mechanism consists of the valence electron in any conduction, they are delocalized while they are away from their atoms, and these freely moving through positive ions, so they are freely moving, and they move through the positive ions like sodium and silver, etc. Now these electrons are fermions. So if you follow their statistics, so that is why there is very little hindrance to electrons' momentum. So their movement, as they are fermions, they will cause very little hindrance to the electron's momentum. So if you take the x-axis only, moment is along the x-axis, so you can say that Vx is equal to h cross kx, and also it will be same for ky and kz. We had considered the movement in the y and z axis, and so there is a ky and there is a kz. Now this kx, ky and kz, they form the reciprocal lattice. Kx, ky and kz, they are forming the reciprocal lattice of momentum space. So now at absolute zero, if k is equal to 0 is the origin, and this is any point in the reciprocal lattice is denoted by, say, kf vector. So at kf, kf stands for the Fermi wave vector. Fermi level is the highest occupied energy level at absolute zero. So EF is the highest occupied energy level at 0K. So corresponding to that, we have KF. So that KF. So we'll try to find out what is the KF is. So EF, as we know, is P square by 2m and PF square by 2m. So it will be H cross square KF square by 2m. This is the Fermi energy. So if you look, this is y is equal. This is equation of a parabola. So we plot E versus K, so it will look like a parabola. Now, if we assume that the sample is in cubic shape, it's volume L cube. The distance between two adjacent electrons in the K space is 2 pi by L. So there is a real space and there is a K space. It's governed by the reciprocal lattice. So if the distance between 2 points in the real space is L, the corresponding distance in the reciprocal space will be 2 pi by L. So larger is the distance between the 2 points, the smaller is the distance between the reciprocal lattice points. Now at 0 Kelvin, the conduction electrons are equally spread out inside the sphere of radius Kf. And the volume of the sphere is 4/3 pi r cube. It's 4/3 pi Kf cube. That means that is the volume in the reciprocal lattice. So if we draw a table consisting of to understand the dimension or the delocalization of the electrons. So for distance L between two points in real space, the k-space distance changes to 2 pi by L, and the Fermi region is twice into kf, because it is in the opposite direction. So this is the center, k is equal to 0. It's twice k because of the diameter. This is kf, and this is also kf. So that is why twice kf. And k square is, if we are considering only one dimension, and we consider it to be say x. So k square is equal to say whether it's kx square, ky square, kz square, any of them, and of course the dimension is 1. This is for L. Now if this changes to L square, so automatically the distance between 2 points will be, in case will be 2 pi by L whole square, and so we are now talking about the area. We are not talking about only the diameter. Initially it was 2 kf. Now we will consider that this is k is equal to 0, and this is kf. Then we will consider the total area covered, since the dimension is 2. So consider it is a circle, so pi r square. So that is why the area will be pi kf square. This is the area, and of course k square will be kx square plus ky square, or it would have been ky kz or kz kx, whatever. And the dimension is of course 2 dimension. And lastly we have L cube, so volume. So it will be 2 pi by L cube in the reciprocal space, and it will be the volume of a sphere, that is 4/3 pi kf cube, the volume of the reciprocal space corresponding to that, because from a circle it will move back to a sphere. So it's the equation volume of a sphere. And of course kx square is now all the 3 components, kx square plus ky square plus kz square, and the dimension is of course equal to 3. Now if you look into this volume, and this is the volume in the reciprocal space, which is actually carrying or occupying the delocalized valence electron. So 4/3 pi kf cube, this is occupying the valence electron involved in conduction. Now again, if we would like to find out the density of states, so the main objective is to find the density of states. For that we need to find out the number of electrons in the occupied region, number of electrons in the occupied region. So if it is the dimension is 1 for single dimension, let's call it as NE. So this is NE. So the dimension is 1, NE is equal to 2 into 2 kf by 2 pi by L 2kf as we have said, k is equal to 0, and this is the position of kf. So since this is always on opposite position, so total distance becomes 2kf. This is where this 2kf comes, and this 2 stands because of the 2 spins of electrons. So this is where this factor 2 has been introduced here. So if it is for, this is for dimension 2, for dimension 1, for if dimension is 2, so it will be again twice into pi kf square, the area, divided by again 2 pi by L whole square. It's for dimension 2, and lastly for dimension 3, we are considering the volume. The number of electrons Ne is equal to 2 into 4/3 pi kf cube divided by the volume, that is 2 pi by L whole cube. Now this is the number of electrons in the occupied region. From this value we need to find out the density of states. So density of states DOS is d of any rate of change of the number of electrons in the occupied region per energy change, and if we apply it for all the 3 cases, then for the dimension 1, the density of states is L by pi into 2m by h cross square. To the power 1 by 2 into e to the power minus 1 by 2. For dimension 2, it is the area by 2 pi into 2m by h cross square. Interesting thing is that there is no energy expression, so this is a constant value. And the third one is V by 2 pi into 2m by h cross square, 3 by 2 into e to the power half 1 by 2. So these are the 3 density of states for the 3 dimensions.